Hello, everybody. It is Wednesday, the 24th of March, and we are in the process of doing confidence intervals. Um, on Monday, we had developed and used one formula. We're going to introduce two additional formulas right now, one of which we will explain today, and the last one we will probably get to on Friday. I doubt that we're going to get to it today. Okay, but I'm going to introduce these formulas to you right now. The first one, okay, when we are doing a confidence intervals, we are trying to be able to say something with a little bit more than 0% likelihood of being true, right? So what we are doing is we do not know what reality is. We do not know what mu is, okay? Mu is a question mark. Mu is the actual average of what we are interested in. We don't know it. So what we do is we take a survey, or we take a sample of products, or we do an experiment or a series of experiments, right? Okay. And if we take a sample, we will look at that sample and we're going to make some inferences, which is why this part of the class is called inferential statistics. We're going to make some inferences about what we think reality is from our sample. Now, X bar is going to be that average from our sample, right? And that will be our best estimate. X bar is our best estimate, okay? But it's only an estimate. It's what we will call a point estimate. It's 1 point. The probability that we hit it on the nose, I mean exactly on the nose. The probability our sample is perfectly lined up with reality is so unlikely it is 0. The probability that our sample gives us the true mean is 0. Okay? By true, I mean exactly. Out to 75 trillion decimal places. Ain't happening. Probability is 0. Right? So what we want to say is we want to be able to say something that our belief of being true is more than 0%. So what we're going to have to do is put a little bit of padding on both sides. So we can say, no, at least I'm 50% sure it's between this amount and this amount, right? Or we are 70% sure, or 80% sure, or 90% sure. The more sure I want to be that I don't say something wrong, the more padding I have to put on both sides, right? And what this formula tells us is it tells us how much padding we have to put on the positive side and how much padding we have to put on the negative side. So what our formula here says is our confidence interval is centered at X bar plus or minus, and this is the amount of padding. The sigma is how much variation there was in the original sample, not the sample, but in the original population. Now this is really weird because it seems like it shouldn't happen hardly ever, but it does, right? And it's really weird that the reason we're taking a sample to begin with is to estimate what mu is, because God, who knows everything, isn't telling us, right? So we've got to go take a sample of it. But magically, even though God didn't tell us what mu was, we have this perfect knowledge of what sigma is. God told us that. Seems weird because it seems like mu would be the easier thing to know, right? Well, it turns out that this happens much more frequently than you think. All right? Where we don't know what the middle is, but we do know what the variation is. Okay? And as one example of this, in quality control, right? There are a lot of machines that every now and then need to be adjusted. Okay? The weights, I've got a scale that basically is, that I weigh food in. So that if I make some fancy recipes and it says for 6 ounces of this, that I can weigh the 6 ounces, right? Every now and then, that zero marker has shifted a little bit and I have to recalibrate it, right? So a lot of times what we will have is statistical tests where we're going to take a sample of stuff and say, oh, is this machine operating the way it's supposed to, or is the calibration off where I have to go back and make sure that zero is really where zero is, right? I've got a scale for food and I've got a scale that I weigh myself. Scale I weigh myself. When nobody's standing on it, it says -6. I still use it because I feel better when I look down and I think that I am under 200 pounds. And I know that if I were to fix the scale, it probably would push me over 200, but the scale's not right. Right? Okay. It's those types of things in business that we have quite frequently, where we're going to take samples, okay, and samples sometimes are above, sometimes the weight is below, has to do with things like what clothes are they wearing, are the keys in your pocket, is there a high pressure system? There's all sorts of miscellaneous gunk that happens on a daily basis and has happened on a daily basis for hundreds of years. Right? We may know that variation. Right? What we want to find out is the scale actually centered where it needs to be? Or is there an error in it? Right? We saw that a little bit on the very first day of class when we had the bullets and the target practice, right? Okay. You guys immediately looked and said, oh, everything is off over to the right-hand side. It's all centered relative. The shots are all over there, but they're all kind of off to the right-hand side. Somehow, what's probably wrong is not the shooting capabilities, the variations. What's probably wrong is that the gun sighting is off. It got bumped or something like that. You got to fix the sighting, right? And those issues happen frequently in quality control, frequently in business. The scenario with the chickens, right? Hundreds of years of chickens. There's a good history of knowing the variation from one day to another. Okay? But what we don't necessarily know is the average, right? Okay? Is this guy selling us big or small eggs? Right. So, live with it for a little while. We're going to live and assume we know what sigma is. Okay? That came from the knowledge we happen to have. Z came from the Z table, the normal table in the back of your book. Okay? It is the normal table z values where x% is between the minus z and the positive z. So this z will correspond to the confidence level you want to make your statement at. If you are doing a 90% confidence interval, this z is the z value that has 90% in between a minus z and a positive z. Right? There's 90% of the area is shaded in the back of the book. Right? If we wanted to do a 95% confidence interval, we would need to have a little bit more padding on both sides because we would want 95% to be in this shaded area. So in a 95% confidence interval, what we want is the z that corresponds to 95%. We happen to know, because we've done this frequently, that the z value that has 95% here has 2.5% in this tail and has 2.5% in this tail. What z value has 0.025? Well, that is 1.96 on the negative side. Over on this side, positive 1.96. Don't believe me? Look it up in the table. Right? If I were to do something other than a 95% confidence interval, if I were to do the green 90% confidence interval, which means I want to tell my boss, hey boss, I'm 90% sure that reality is between these two numbers, I would use a z that corresponds to 90%. And in that case, minus 1.645 and a positive 1.645 are going to be the z value. Okay. The z value talks about the confidence level that you're trying to do. Okay. You want to have a 50% confidence level, a 50% confidence interval will have a z that has 50% in the back of the book between the minus z and the positive z. Different combinations will give you different z values. Okay. So we know what that is. We can look that one up in the back of the book. This being what I'm pointing to is the z. The sigma we are given to us by the problem. Somehow God spoke to us and we know what the sigma is for this population. And n is the number of observations in our sample. Okay. I'm going to look at fish in Baffin Bay, and I'm going to go out and collect 100 of them, then n equals 100. If I'm going to go look at 4 of them and make the best choice I can make out of 4, right, then n is 4. Okay? It's however many samples I have. Okay? So how do I get my x bar? I add all the x's together that are in my sample and divide by n, right? If you guys took 4 tests this year and you had to come up with the average, what are you going to do? You're going to sum up all the x's and divide by n. N is what? The 4 tests for the sample of 4. Right. All right. So that gives us our first equation. Now I said there's going to be a second. Well, I'm going to say there's going to be a third. We'll get to this one Friday. The second one looks identical to this one. Okay, with one exception. Okay, and that exception is where there's a sigma up here. There is an S right there. Since this formula doesn't have the sigma in it, but has the S in it, what is the S? It's the standard deviation from the sample. Why am I using S instead of sigma? Well, maybe I don't know what sigma is. Right? What is my best estimate of what the variation is in the population as a whole? Well, I don't know that, but I have observed how much variation there is in my sample, right? We're going to use that as our estimate of sigma. So S is our estimate, our best estimate we can make of sigma, right? So when can we use this? And it will turn out that it will be okay to use the second formula. I'm going to get rid of everything else that's kind of in its way. I'll just rewrite it. Rewrite it is probably easier. The second of the formula is going to be x bar plus or minus zs square root. We use this when sigma is unknown. Okay. If we knew what sigma is, why would we use an estimate when we knew what reality was? Right? If God told us what the standard deviation was, we're not going to tell God, thanks, but no thanks. I can calculate what it is from my sample, and I know my sample's not perfect, but I'd rather use my sample than use what I know is true. That's garbage, right? If you know something is true, you're going to use it. You only will estimate it if you don't know what the real number is, right? If we don't know what the real number is, we're in this situation. Sigma is unknown. And we will just plug it in. We will use our estimate, S. Now, are we going to guess S correctly from our sample? The probability that we hit it exactly on the nose is 0, right? But you know what? This is statistics. We're never going to have everything perfectly right. Yeah. So what happens? We will say, just plug S in and pretend like you knew what sigma was, and everything will be okay. Well, you can only do this when n is large. If n is large, we can feel relatively comfortable. If n is large, we can feel relatively comfortable that our estimate for sigma is going to be reasonably good. Okay. Now, I got a question to the class. What would you consider to be a large n? Anybody just put in your comments, what's the answer? What do you think when I say it's okay to use this formula when the sample is large? What do you guys think large means? 5, 1,000, the whole population? Well, if we do the whole population, we have done a census, and then we know what God knows, right? So far, I've got an estimate of 1,000. Anybody want to come down from that? 1,000's too high. 10. Yeah. Now we're too low. Any other guesses? 100. Okay. 100 is too high. It will turn out that the magic number in statistics is 30. If n is 30 or more, okay, what we are going to say is our estimate of S is going to be pretty close, good enough for government work. All right? Government and statistics work, right? So if we are in a situation where sigma is unknown, but our sample size is relatively large, what we're going to end up doing is using this formula, just substitute where there used to be a sigma, just substitute S and pretend like nothing happened. Okay? Yeah, it's technically not right, but it's not going to change the outcome noticeably. We're just going to go with it. Okay? Which leaves the question, what happens when n is less than 30? Well, that's when we're going to use this formula on the bottom, and that's the issue for Friday. So if n is larger than 30, we're at this one. If not, we're up here. But the formula's pretty much the same. Oh, by the way, what's the difference down here? All of a sudden, we're not using the z from the z table. We're going to need to go to the t table, okay? Because our S isn't completely right and we don't really trust it. We've added more uncertainty to the equation, and adding more uncertainty makes that bell-shaped curve seem a little wider, and we will actually use a different bell-shaped curve, which is the t distribution. Okay, but as I said, that's Friday. All right, so let's do a problem or two. All right, so let me go see if I can find one in the book that we can use. By the way, I think I will put a homework assignment out there. Maybe I won't necessarily use the exact intervals. All right. I'm on page 245. I'm going to be number 15. According to a credit monitoring agency Experian, the population of consumer credit card holders carries an average credit card balance of $5,500. With a standard deviation of 750. You plan on drawing a random sample of 625 cardholders from this population. What is the probability that the average credit balance for the sample is somewhere between 5450 and 5550? Okay, I got to the wrong page. All right, let's use some of that information and do a confidence interval. Right? I took a problem before the book got to the confidence interval. So let's just do what the study did. Okay. Well, I'm just going to make this one up. We are going to start with the idea that we take a sample of 625 n equals 625. Sorry, you can't see that. I'll bring that closer to me. Okay, and our average debt is 5480. Let us assume that we know what sigma is. Sigma equals 750. Right? So, from the 625 random Americans, okay, that I chose, what is our best estimate about the population? And it's this one here, 5480. X bar, our best estimate is 5480. Now, we know that we are going to be wrong. Reality might be a little bit above us, or reality might be a little bit below our estimate, our average we got from looking at these 625 people, right? So we have, this is our best estimate, and then we're going to put padding on the plus side, and we're going to take the same amount of padding and put it on the minus side. So plus will go on the right side, minus I'm going to subtract off this amount of padding. Well, let's say I want to have alpha equals 95%. So I want to do a 95% confidence interval. Okay? 95% confidence interval means I want to be able to make the statement to someone. I am 95% confident that the average indebtedness in America is between these two numbers. Right? We know it's centered around what our sample said, but we need to figure out what the padding is. What is the z value that corresponds to 95%? 1.96. Right? So that is the z. What is the sigma? The sigma was 750. How do we know that? Because God told us that. Somehow it would have been in the problem. If it wasn't in the problem, we'd have to go back to the sample and calculate what S was, unless somebody already calculated what S was for us. And sometimes you'll see that in the problem. Instead of a sigma, you'll see an S. All right. So in this case, we know what sigma is. What is our N? Our N was 625. We'll get square root of 620. So let us calculate this. All right. So I am going to turn on my calculator. Control calculator. All right, so I got my calculator up, and I am going to shift this so that we are looking at my calculator. Share camera, share applications. All right, if somebody could just verbally say, yes, Professor, we see your calculator. They may see it.
Yes, sir.
Okay, thank you. All right, so the first thing I want to do is take the square root of 625 because that seems like so 625, 625. Here's the square root button. This should hopefully do it for us. Okay. Oh, I have to be on the calculator. Okay, the calculator button is square root. Gives me 25. So 25 squared is 625. Square root of 625 is 25. Right? So going back to sharing the camera, plug that in. So we know that the square root of 625 is 25. What is 750 divided by 25? Okay, go back to the calculator. Okay, so let me clear everything. And it clicks, but it doesn't do what it's supposed to. Okay. 750, 750 divided by 25 is 30. Okay. So stop sharing. Okay, so 750 divided by 25. What did I just say it was? 30? Okay. So the next thing would be our confidence interval is going to be 5480 plus or minus 1.96 times 30. Okay, 30 times 1.96 is your application screen. So we had 30 times 1.96 equals 126. Okay, so all of this whole thing here is 126. Okay, so our confidence interval is 5480 plus or minus plus n minus 126. So on the negative side, on the smallest side, it's going to be 5480 minus the 126, which is 5, 2, no, 5, 3, 5, 3. Last one is 4, 7. So on the low side, it's 5, 3, 5, 4. On the positive side, it's 5480 plus this. So that would be 5, 5, 5, 6. Did I do that math right? 5480 plus 126. Add that 604. Yeah, you got that right. Okay, so I can say, after having looked at these 625 people, that the average, that the reality, that the real average, I am 95% sure that the reality is that the indebtedness in America is between $5,354 and $5,606. I am 95% sure that you, the real, honest to God, American debt level is between these two numbers. I am 95% sure, and therefore I just gave you an interval, a 95% confidence interval of what I am sure it's between those two numbers. Is there a possibility I'm wrong? Well, what was the likelihood I said I was right? It was 95%, which tells us there's a 5% chance you got it wrong. All right. So let's change things around and do this problem over again. In this case, let us assume that we got a different sample and that we got 5,500, but we only took a sample of 36 people. Okay. Let us assume that we still know that our sigma is 750, and let's still assume that we are looking for a 95% confidence interval. Okay. All right. So this is something that you would have needed to know before you did a confidence interval. If somebody doesn't tell you what level, assume that they're going to mean 95. 95% of the time, people need that mean 95 even when they don't tell you. It's kind of the default. But if somebody tells you they want a 90% confidence interval, give them a 90% confidence. All right? Okay. We know what sigma, you know what? We don't know what sigma is, but our sample was S. Okay? S equals 750. Okay? So we go up here and we say, we know what sigma is? No. So we can't use this formula. We have to use this formula because we know an S instead of a sigma. Other than that, 1 and 2 are the same formula. So we're going to use this one. What does this work out to be? What's X bar? 5500 plus or minus, again, the Z that corresponds to 95% confidence interval times sigma, nope, we don't know what sigma is, times S square root of that. Right? We can use this because sigma is not known, and we're going to use S, but N is large. Why is N large? Because 36 is more than 30. Okay? So plugging these things in, square root of 36 is going to be 6. S is 750. Okay. Z that corresponds to 95%, again, is this 1.96. Plug that in. Now, all we have to do is start multiplying those things out. Okay? We'll start getting rid of that fraction. What's 750 divided by 6? Okay. Applications. Okay. 750 divided by 6 equals 4,500 times 1.96. Okay. So it's 5500 plus or minus 8820. All right. Let me just check to see if this makes sense.
Professor
Okay.
Schumann?
Yes, did I make a math mistake?
Yeah, 750 divided by 6 is 125.
Is 125. Okay. That makes this number look a lot more reasonable. Okay, so what's 125? What's 125 times 1.96? 125 times 1.96. Yeah, those numbers look like they were going to be overwhelming. Like I made a mistake. 245. Okay. Okay. All right, you guys should be seeing me again, right? So what do we have? The 95% confidence interval now is $505,500, which came from our sample down here, from our X bar, plus or minus 1.96 times this fraction, which was 125. So plus or minus 245. So on the low side, we have $5,255. On the high side, we have $5,745. So we can say, after we took this sample of 36, say, well, of our 36 people, we came up with an average of 5,500 plus or minus $245. So we are 95% sure, we are 95% confident we're in between those two numbers. Okay? You guys sort of understand that. Now, when it comes to doing these types of problems, okay, and I'll put a couple problems out there for homework, all right? The thing that I see on tests falls into a couple categories. One is the three categories. One that really gets it and figures out the rules pretty quickly, figures out what goes where, right, and gets it right. You've got some of you who get completely lost. Hopefully that's going to be relatively few of you. And then what gets me the most is people get to the formula and they don't know what number to plug in to what spot. The Z value is always going to come from the table in the back of the book, either the Z table or the T table on Friday. It will turn out you can actually get the Z value from the T table and it's easier, right? So you get the Z from the back of the book. You can usually get it from the T table, and we'll go over that on Friday. Right? S and sigma are usually given to you in the write-up of the problem. It will be described. What is sigma? It is the population standard deviation. What is S? the sample standard deviation. Those things should be given to you. If you're doing your own analysis, you may have to calculate what S is, right? Okay. We did that in the first week of the class. Typically here, somebody has already done that and given you the X bar, and there's this bar hidden from you. All right. This is what the results were. That is the mean of the observations. And N is how many observations we had. What gets me and it makes me pull my hair out is people will substitute N for all sorts of stuff. Okay? Or they can't figure out what N is. N is the size of your sample. Okay? And S or sigma, standard deviation, or S's and sigmas. And believe it or not, I guess it's the pressure of taking a test. People's brains sometimes go to mush. All right. We are pretty much out of time. What we are going to do on Friday is we are going to do that third formula. What happens when you don't know what sigma is and N is small? And now you're going to have to use what is called the student's t-distribution instead of the standard normal. So we will do all of that on Friday. And then next week, we're going to do two special things. One is what to do when you are doing confidence intervals for ratios or percentages, right? There's a separate formula for that, okay? And then we will look at confidence intervals for differences between two things. A lot of times we will be in the world of, I like to talk about it as left Twix and right Twix plants, right? And we're going to ask the question of, are these two machines doing the same thing? On average, if these two machines were programmed to do the same thing, each one of them is going to have a little bit of variation, okay? But we're going to look to see how much the variation is. Now, ideally, it'd be centered around 0, right? How much variation there is. Or we will look at pre and post numbers. I'll take the example of the school teacher, right? And I'll take students and I'll check their reading level at the end of the 3rd grade, and I will check their reading level a year earlier, and that delta will be how much the teacher that year was able to bring that student up, right? And we may want to say, okay, on average, the school teachers in Kingsville bring people up how much in an academic year. Okay, we can check that type of stuff out. So those will be the things that we will do next week. And then we're going to have a test on confidence intervals. And it will probably we'll probably have that test a week from Friday. No, probably a week from Monday. Okay. So you'll have a bunch of opportunities there. And then we will go to the next section, which is hypothesis testing. Anyways, this is it for today. I started with the 3 formulas. We did the first 2 today. We will do the 3rd one on Friday, in that we will introduce the t-table to you guys on Friday. All right, with that, I'll let you guys go. See everybody on Friday. Are there any questions?